So we've been talking about Newton's law of heating and cooling, and I've got one more example I'd like to take a look at. At 9 a.m., an object at a temperature of 73 degrees Fahrenheit was placed in a 500 degree Fahrenheit oven. By 9:15 a.m., the object's temperature had increased to 166 degrees Fahrenheit. Find a model for the object's temperature T in degrees Fahrenheit as a function of x in minutes after 9 a.m. So this is a Newton's law of what have we got here? We are heating, right? So we have Newton's law of heating. Question. But one thing that might throw you off is that this information is not given in tabular form. In other words, the problems that we've seen before, you actually had a table written out with all your objects and all your temps, and you don't have that here. But we essentially still have that. We just have to make the table. And in addition, the table is going to be a lot smaller because we don't have as many points. But what points do we have? Well, we know at 9 a.m. the object was 73 degrees. And then at 9:15, the object is 166 degrees. So our table is just going to consist basically of 2 points. And remember, this is going to be an elapsed time. So we'll start at time 0. And at time 0, you're at 73 degrees. And then at time 15, because we're going to do this in minutes, we're going to be at 166 degrees. So that's our table. And then we can also, I'm just adding object temp right there. When we actually do this in the calculator, remember that we're gonna use the PTD. So ultimately, what we'll have is for L1, we'll have 0 and 15, and then for L2, you can just go ahead and do the and calculate the PTD right here, because it's relatively easy to do. So maybe I'll just do that. In the other examples, we made L2 be the column of object temperatures, and then we had a third column and did the PTD of that, which meant that when we did the regression, we had to do L1 and L3. If I just do it in column L2, then I don't have to change my regression. It doesn't matter either way. Just remember how you're approaching it. So the oven is 500 degrees, so this is going to be 500 minus 73, and this is going to be 500 minus 166. That's easy enough to do by hand. When I say by hand, I mean just to type these in. It's only 2 subtractions. So, all right, so that being said, let's actually go ahead and develop our model. So L1 is 0 and 15. L2 will be 500 minus 73, then 500 minus 166. And now we're going to do exponential regression. Now this is still going to be the PTD function is what we're going to end up finding when we do this regression. But we're going to do exponential regression. And now we can just do L1, excuse me, and L2. Okay. So there's our PTD function. 427 times 0.984 to the x. That's your PTD of x. All right. Now, remember when we're doing these, we actually want the object temperature function. That's ultimately what we want to find. And so to do that, we're going to need, since this is a heating problem, remember that the PTD relationship, what is it? It needs to be positive. So the room in this case is the oven. So it's the room minus the object. So that will give us our correct PTD relationship. And so then when we solve for object, the object function, I'm adding this to the other side and subtracting this from both sides, so we end up with room minus PTD, which in our case is going to look like 500 minus this 427 to the x function. 500 degrees is the temperature of the oven. So when I say room, I mean oven. All right, so we just need to do that in the calculator, which means I will go to second, insert 500 minus, and now we actually have our object temperature function. So if I put in an x value, that'll give me the temperature of the object after so many minutes. Now, the way this is solved in the notes, we're actually using the old new old formula, as you see here. And this is fine. I encourage you to read through this, and if you prefer to do it this way, that's absolutely fine. But you know, we already have exponential regression at our disposal, and it works perfectly well with 2 points, as it does with 8 points or however many. So we can just use that instead. At least that's what I'm going to do. So I have also this alternate method presented here, and that's what we just did. We did the alternate method, and that was our answer. Okay, so now we can use this model for some stuff. So for example, what will be the object's temperature at 10 a.m.? So remember, we started at 9 a.m., so that's 60 minutes. So all we have to do is just evaluate the model at 60. And that's our object temperature, 340.15 degrees Fahrenheit. Okay. Question B, at what time to the nearest minute will the object's temperature reach 450 degrees Fahrenheit? That's a calc intersect question, because 450 degrees is an output of the function. So we'll go to our function list and add 450. And we want to know how long it takes to do this. So in terms of your window, we can certainly go to the table and get an estimate there in a very accurate way. But another thing you could do here, just to show you another kind of looser method of doing this, is I already know that 60 minutes gets me to 340, so I need to at least go beyond 60. So maybe we'll just make it a couple of hours. Let's go to 120. That's probably fine. And then do zoom fit. And if this gives you trouble, we can just go to the table and actually scroll through and find a more accurate X max. So we'll see if that was a... Oh, I didn't go enough. I didn't go enough. So you know what? I'm going to go ahead and go to the table. But I do need, since my table needs to start, let's start our table actually. Let's start it at 100 so I don't have to spend all day scrolling. And there you can see. I mean, I was pretty close, but not close enough. So we need to go up. We're trying to get to 450. So that happens at around 130. So I just need to go, maybe, let's go to 180. Let's make it 3 hours in the oven. 180, and then we'll do zoom fit again, and that will be sufficient. And then once we get our graph, we're just going to do calc intersect and find the intersection point. So it's still kind of high up there, but we can see it. Okay, there it is. 130.97 minutes. And 130.97 minutes. So time-wise, that's a little more than 2 hours. So we started at 9 a.m. So that's going to be 11:10, 11:12. 1111, 130.97. Okay, so that completes section 5.3 in our discussion of Newton's law of heating and cooling. I do find that people tend to miss these problems a lot, and I think it really comes down to understanding the fact that we have an extra step that we have to do, which is this PTD step, and understanding how the PTD relates to either room minus object or object minus room. Right, and for room minus object, that would be when we're heating up, and for object minus room, that's when we would be cooling down in order to keep this positive, and just understanding how to use this relationship in addition to the regression. All right, so as I said, that's the end of section 5.3, and from here we'll go into 5.4.